Hey everyone, welcome to this course. This is Machine Learning, Hardware and Systems. It's the first time this course is being offered here. And as I previously said before, I'm a new assistant professor at Cornell Tech, and so this is actually the first course I teach here. So I have taught before, don't worry though. So hopefully I can get you excited about machine learning, hardware and systems in this course. The main idea is that you hear about artificial intelligence and deep learning and machine learning, and it's making changes across the whole world. But the way it actually runs is through hardware and through systems and through optimizations that we'll learn in this class. So in CS, you may take a course that teaches you this stuff at an algorithmic level, but how do you actually make it run on a computer? And how do you build that computer that runs it is what we will try to learn here. So let me try sharing my screen. Okay. Okay, so this is lecture 0. We will kind of just go over logistics of the course. Feel free to stop me at any point and ask me questions. And then a very brief introduction and motivation on why we are kind of here and why we're learning this. So I'll start by just one small motivation slide, and many of you may know this already, but a few people at Google, very highly paid people, very smart people, in 2013 they sat down and said, if we have our users use our deep neural networks for speech recognition for just 3 minutes every day, then we will need to double our data center capacity. That means, going and building, 2 times what they have of those huge buildings, with their power plants beside them or the wind, turbines, as you can see here. So doubling that whole capacity just to support 3 minutes of speech recognition. So what does that tell us? That tells us that this thing they want to run is very heavy computationally. You need to double your computers just to run 3 minutes of it, then it's very heavy. The second thing is that it tells us is that existing data centers suck. They don't work. They're not good for that type of application. And so what the folks at Google did, as I said, they were very smart. And so they didn't do that. They didn't go and build, twice the data centers they had just to support this new application. Instead, they built a custom chip. So that's what led to kind of the TPU being designed. And what they achieved by rethinking the hardware that runs this program, they achieved 1 to 2 orders of magnitude improvement. So 10 to 100 times improvement in this specific workload, speech recognition. And so compared to existing CPUs and GPUs. So they didn't have to go and build, twice their data centers. They just created this new chip and put it in their existing data centers, and that was enough. And so to make this chip work, it's not just about designing the hardware, it's about a lot of things. And we will talk about hardware. So approximately a quarter of this course is hardware architecture. How do we analyze existing hardware and compare existing hardware to each other and see which is better for each workload? How do we achieve an efficient hardware architecture as well? And we will go a little bit into microarchitecture, or how we build the circuits to do the actual math and maybe even memory for these kind of chips. So we'll touch a bit on that as well. So the course is called Machine Learning, Hardware and Systems. So we will also discuss some systems. So once you have this one chip, how do you put them together to train deep neural networks in a distributed fashion? So distributed training is very important, especially for extremely large models that we're seeing these days. So how do we do that, and what does it entail? We will also talk about federated learning, which is another way of distributed learning, but through kind of which has some security guarantees for end users. So for example, if you have your mobile phone and you have data kind of streaming out of that phone, how do you use that data to train a neural network securely and privately, and aggregating this data from kind of users all over the world with different kind of properties and so on. So that's federated learning. We will also talk about deep learning systems in terms of also what happens around the neural network. So the pre and post processing that we have. And finally, we'll discuss some environmental issues as well and kind of the carbon footprint of all of these systems that people are building. So it's actually not enough to just talk about hardware and systems in isolation, because there's a lot of work that's being done in like upper layers of kind of the software and algorithmic stack. So at the neural network level, we will also discuss how to realize an efficient neural network that is tailored for hardware, that works better for specific hardware targets. So we will discuss kind of things like quantization, so using lower numerical precision for numbers in a neural network. We'll discuss pruning and sparsity, and techniques like knowledge distillation to create more efficient neural networks. And finally, automated machine learning, specifically neural architecture search, or how do you find the best neural network topology for that fits a specific hardware especially. And finally, we will talk about software. So hardware is useless without software, it's a brick. So how do we program these new chips that we will learn how to build? And there we will talk a lot about these new domain-specific languages and compilers that are sprouting specifically for deep learning. And there are domain-specific languages and compilers for other applications too. For example, there are some focused specifically on computer vision, but an emerging class is just focused on deep learning tasks more generally, and not just for one kind of domain or one modality. So these are kind of the 4 course topics. And I think every bullet point here kind of translates to one of the lectures. So if there are any questions at this point, just stop me and let me know. Otherwise, we can continue. So I told you kind of why it's important to learn about you know, a deep learning hardware and deep learning systems. And I told you what we will cover. That now I'll try to convince you that I'm the right person to kind of teach this. So I'll tell you a bit about myself. So my name is Mohammed Abdel Fattah. I'm a new assistant professor here in ECE at Cornell Tech and Cornell University. And I thought I would tell you kind of briefly where I've been in the past few years. So I'm Egyptian, I'm from Egypt, and that's where I did my undergrad. If this animation works. At the German University in Cairo, so that was a long time ago. And then after that, I went to Germany. At the University of Stuttgart, I worked on my master's there. And there I started focusing on hardware architecture, especially FPGAs and reconfigurable hardware. I continued that interest kind of as I went and did my PhD at the University of Toronto. And there, I focused on computer architecture. So most of my training and background is in hardware. But then after that, I didn't want to go straight into kind of an academic job. And I thought that I really needed some industrial experience to see what's happening out there. And that's kind of when deep learning was exploding. And so I started working at Intel in Toronto as well, where we built the first deep learning-based accelerator on FPGAs. So we built both the hardware, the software, the compiler for that. I stayed there for 2.5 years, and then I went to Samsung. They were creating this new AI center in the UK. So I helped form the team there. We worked on automated machine learning, and more generally, how do you create efficient machine learning models to run on Samsung phones, basically. And that was a lot of fun. I stayed there for 3 years. And then now I'm here. I'm at Cornell Tech. And so hopefully throughout the lectures, I can also kind of transfer to you some of this industrial experience and what the real problems are that I saw in industry. So I'm also very fortunate to have a TA with me. So that's Guandao Yang. And he's an expert on computer vision. I think he's a 3rd-year PhD student at Cornell Tech. And he will be helping mainly with the assignments, especially kind of the heavier assignments that have a lot of kind of moving parts. I don't think he's here today, but he's a great guy, and he has some amazing research papers out in top computer vision conferences. So he'll be a great resource to ask questions as well. So throughout kind of the past term, I also had the help of these amazing 4 people in just preparing the assignments and the kind of the programming parts of this course. So thanks to Rebecca, Zanshi, Yauki, and Alan. So they're not part of the course anymore, but throughout the past kind of 5 or 6 months, they helped a lot in kind of shaping what the assignments look like. Okay, so the prerequisites for this course. So you should know something about computer architecture fundamentals, because we will build on some of that. So we will selectively choose some topics that are relevant for deep learning accelerators and build on those. So you should know something about that, right? Like if you know nothing about computer architecture, you should be slightly worried coming into this course, and maybe chat with me or drop me a note by email. You should also have already kind of taken an introductory course in machine learning, or you know something about machine learning, because we won't cover the fundamentals here, but we will build on many of them. So you should also have already kind of trained the neural network. You should have run a neural network. You should ideally know PyTorch, and you know you coded something in it before, and so on. So if you have any issues with those prerequisites, just let me know upfront so that we can kind of chat about it. We will use a textbook in this course, but we will also read a lot of papers. So the textbook is called Efficient Processing of Deep Neural Networks. I think it was published last year or the year before. So it's available at the Cornell University Library. If you just search that title in the kind of the online library portal, you will get to a page where you can just click on this link here, and you will be able to download a PDF of it. So very simple. So you should be able to all access it. Again, if you have any issues with accessing this, let me know. So evaluation. So this course will be very top heavy. Most of the grades will kind of be on the assignments that are done throughout the course, way before the finals. So in finals week for this course, you won't be that busy, but during the term, you will have all of these heavy assignments. Each one of them is like a mini project where you will get kind of hands-on experience of doing these optimizations or doing the compiler stuff, or maybe doing some hardware research and so on. We will also have a term paper, so that will account for about 20%. A presentation, which is a 10-minute presentation on one paper. Ideally, hopefully, will be in person by then. So that will account for 10%. We will have weekly paper summaries. So I think you should read the papers anyways, because then if you don't read the papers, you won't get kind of the full pictures of what we're trying to cover in this course. But I also ask that you do a very brief paper summary, less than half a page, every week, and it will count for about 5% total. And finally, class participation. Yeah, and as I said, this is the first time this course is being offered. No one is perfect. So if you find any errors or bugs in the lecture notes or the assignment material, and I'm talking about major things, like not typos or anything, but if you find something and you're right, then you'll get bonus points. So if you correct me on something I say or something I put out in the lecture notes, you get bonus points. Everyone's happy. So yeah, I'll go briefly through every one of those and talk about it quickly. But again, just stop me if you have any questions about any of those things, or if you need some more clarity into it. So the assignments, as I said, they account for most of the course. Assignment 0 will be out today. It will be sent on your email through a GitHub Classrooms link. And it's basically like it's a very simple assignment. It's worth 2 marks. And it's just kind of knowing the design tools and the programming tools that we will use so that you kind of know these things up front and you don't have any issues with them later in more involved assignments. Assignment 1 will be focused on hardware. So we will do a lot of hardware benchmarking and some hardware research and plot properties of this hardware on something called a roofline plot that we'll learn about next week. So, the third assignment is quite beefy. It involves kind of training and optimizing a neural network model and then actually deploying it to a small MCU, a small microcontroller unit that I have up in my office. So you'll borrow that MCU, you will deploy the model on it, you will test it with your own voice and see that it works, and iterate and do optimizations there. Assignment 3 will be focused on kind of software compilation. We'll use a tool called TVM. And assignment 4, I was hoping it would be hardware design, but I realized that if towards the end of the course, I get you to learn a whole new thing and to design hardware through something called high-level synthesis, that will be too much. So instead, we'll do something else, which actually turns out to be super interesting as well, which is implementation of different, and also approximations of different DNN primitives. So there are many ways in which you can implement a convolution algorithmically. And so we will implement those different implementations, and we will see how they run on different hardware targets. So it actually turned out to be super interesting. So the term paper, you will kind of go over a topic of your choosing. So we will coordinate that topic, just run it by me at any point, and I will talk about that more during the term and give deadlines and so on. But basically, it will be kind of a critical assessment of that topic, focused on 3 or 4 papers, and maybe covering at least 10 research papers on that topic. And that will be due kind of after finals week. So that's at the very end of the course. You will also do a quick presentation. So it will be a 10-minute presentation in class. So it should cover mainly 1 paper or 2 papers. Ideally, those would overlap with the papers that you select for your final paper, so you don't have to do the work twice. And also, again, it should be a topic you're interested in from the things that we're discussing. Finally, paper summaries. So, so the reason we have kind of assigned papers every week and these paper summaries is that, you know, this topic is kind of changing every 6 months. So we need to kind of stay on top of research. Even when I was working as an engineer at Intel, we would basically read the paper and implement the idea in our deep learning accelerator. So it's not a matter of just knowing the stuff in this course and that's it. No, you have to also master kind of reading papers in this topic and staying up to date with research to be able to do well in this, whether you're going to an industrial job later or further graduate studies or something. So yeah, so you only have to do 10 of those, or you only have to submit 10 of those paper summaries, but feel free to do more. And the top 10 will kind of go towards your grade. Each one is worth 0.5%. So it's kind of just, you know, you hand it in and that's enough, but you should at least cover those questions. And as I said, it should be like a maximum a 1/2 page, so nothing major. I mean, if you want to write more, then sure, but it doesn't matter regarding the grade. So class participation. So I'm hoping the class will be interactive. So each one of you should kind of contribute an idea or ask a question if you have a question. Initially, I had this saying every week or every class, but yeah, maybe that's not practical. So you don't have to talk in every class, but every now and then, hopefully, you'll kind of interact and say something. So. Course tech. So we're actually using a bunch of platforms, but hopefully it should all be streamlined through the course webpage. So all the important links will be there. So the Zoom link is there, the discussion link is there, the Gradescope link is there. Yeah, so these are kind of for the logistics and kind of the in-class recordings and everything. So that should all be accessible through the webpage. I think I will also put the recordings of these lectures on the webpage. Maybe you'd need kind of a Cornell email to access them, but yeah, everything will be accessible through there. I didn't want to use Canvas really, so we won't really use that for much. Yeah. And then for the assignments, we will use GitHub Classroom. And so for that, I think I will send each of you a link for the assignment as soon as it's out. So after this class, I'll go up to my office and release assignment 0. So I'll take the class roster and send an email to everyone with a link to assignment 0. So if you have any issues with that, or if you didn't get a link or something by the end of today, just let me know. And even if you're auditing, just let me know and I can send you that link. It's no problem. I just won't grade it. That's fine. And for coding, we will use Google Colab. And that's mainly for convenience. I realized we don't have access to kind of GPUs for teaching at Cornell Tech yet, which is something I hope to change. But basically, until then, we will use Google Colab. It's quite convenient. It kind of opens up a Jupyter notebook on one of Google's servers, and you get to kind of basically, act as if you're on a computer with a GPU, basically. And so I recommend buying Colab Pro, especially starting assignment 2. So it's $10 a month. You don't have to, and I've definitely went through the assignments myself without buying Colab Pro, but it will help because then you can have models training in the background and so on. And so I think this will be quite convenient if you're using for Colab Pro, for Colab. Basically, it will make it a lot easier for you to kind of go through, especially assignment 2, which has a lot of training, pruning and quantization and things that take time on a GPU, basically. Course philosophy. So as I said before, this course needs to kind of stay state-of-the-art and research heavy. So we will be discussing papers in class, in the lectures. You need to read papers after every lecture to kind of stay up to date with everything that we're talking about. All of this stuff is being defined as we speak. If you're going to work in this, hardware or systems for machine learning after you finish your degree here, you will be inventing what's happening next. You won't be working on something that's already established. And so, as I said, we really kind of need to stay up to date with all of these papers and all of this research that's going on. The course is practical, so the assignments have a lot of kind of hands-on coding, and that's on purpose, obviously, because this is a very applied subject. If you learn about something by just being told or reading about it, that's not enough. You have to go there and see all of the details and code it yourself, and that's what you'll be doing. It should be fun. So the assignments, I hope, will be quite fun. Hopefully everyone here likes coding. Otherwise, you need to kind of question why you're doing a master's degree in ECE or CS. But I think the coding that's assigned here is quite fun. We will also maybe have 1 or 2 competitions on the submissions of the assignments. So we'll kind of have a leaderboard and see who kind of has the best result. So maybe this would also be fun. But yeah, honor code, we're all adults, don't cheat. If you use something, cite it. And it's okay to discuss ideas with your colleagues. That's definitely okay. I read this research paper. It had this implementation. This is slightly different than what we learned in class, but I think it's interesting. But I implemented it this way, or I had this bug, but then it's very easy to solve it if you use this library, something like that. But going in, looking at someone else's code, copying code, that's not acceptable, right? So there is kind of a distinction between discussing ideas and copying code, and hopefully you know that distinction. If you don't, you can click on this link and it has kind of details of what is considered acceptable and what is not. We will use various tools that check the code and the text of the assignments for plagiarism. So please don't copy anything. Yeah, and I think that brings me kind of to the end of the logistics part of this course. So here are the topics. Once again, here is the kind of the evaluation, how we will grade this course, and here's the class website. So I want to stop here for kind of a couple of minutes. And does anyone have any questions or concerns about any of this, or any comments even? Yeah, it's harder when I can't see people. So, but I'm assuming silence means everything is quite clear. Oh, chat. Yes, chat. All good. Someone said all good in chat. You can also use chat I think I know how to access it now. So thank you, Gonzalo, for saying all good. Okay. All right, yeah. At any point, again, feel free to interrupt me. This is supposed to be a bit more interactive. For weekly readings, okay, so we have a question from Hayden. For weekly readings, does this only count the academic papers or does this include the book chapters? So only the academic papers. So the summaries are for the academic papers, the book chapters, you should read them anyways, because that's the textbook that we're following in at least half or 2/3 of this course. So I'm hoping to see summaries of the research papers that I link to on the website. Okay. Okay. All right. I will continue. So now a brief introduction to the course. It's 10. Okay. It's 10 past, so I think we have time. So I'm sure you saw this many times before, but what is machine learning? What is deep learning? What will we be covering out of that circle that's labeled artificial intelligence? And so, machine learning is a subset, a strict subset of artificial intelligence, right? Like it's a technique to make machines learn or programs learn how to perform a specific function. And one of those techniques, and one of the prevalent techniques there, is neural networks. And then you have deep neural networks, and that's actually what we will be focusing on. So the course is called Machine Learning Hardware and Systems, but it could have easily been called Deep Learning Hardware and Systems, because that's what we will focus on. How do we take those deep neural networks, build hardware, software, compilers, systems for them, and train them properly? So this is where we'll be focusing. So what is so special about deep learning? Like, why are we creating this whole course just to discuss how hardware is built for it and how systems are designed? What's special is that it's been making breakthroughs in many application domains. So recommender systems, any kind of online software that we use now, Amazon, Google, Facebook, all of these companies, their bread and butter is having these recommender systems. So getting all your data, parsing it in some way, and recommending products to you, or recommending money-making kind of schemes for you. And so, or even telling you what to watch next based on what you already like, or like on Netflix. So these recommender systems are super important and have been increasing in importance throughout the past decade. In computer vision, of course, that's where many breakthroughs are being done as well. So self-driving cars may be one of those results. Things like image segmentation, image object detection, image classification. These algorithms have exceeded kind of human performance given using these neural networks, and so huge breakthroughs there using deep learning. Speech recognition as well. We're able to fit that on kind of devices as small as Apple Watches or even smaller devices now. And then natural language processing as well, which is making huge waves in things that, okay, like translation and text to speech and things like that, but also in application domains that you can't even dream of. So I have a friend who was working at Reuters, which is a news company, and what they are doing using those NLP models is automating paralegals. So paralegals are they're people who help lawyers draft out documents and so on. Now they're actually replacing these paralegals with NLP models, because a lot of their work is making very standardized templates and things like that, and they're able to use these NLP models to parse through thousands of or millions of legal documents and draft those new legal documents automatically. So NLP is actually a big application, has a lot of applications these days in many application domains. There are other applications, of course, that maybe I don't know as much about, but things like finance, definitely in healthcare, and computer vision has a huge role to play there in detecting things from various scans, like tumors on X-rays or things like that. in computer games and graphics, and in agriculture as well. So deep learning is making waves in all of these things. It's changing the way we think about these applications, and it's moving towards kind of a deep learning centric way of doing things. So no longer do people write software by hand. Instead, they rely on these deep learning models and they just build a system around it. So for all of these important applications, we have kind of, as I said, you can't run these systems without hardware. So in the example of the Apple Watch or any kind of mobile system, we have the small part of the chip dedicated for a neural engine or an NPU, neural processing unit. And so, you know, how do we build that hardware? How do we compile software onto that chip? So that's super important. In vision, of course, maybe some of you have heard of Tesla's FSD chip, so full self-driving chip, and they're not the first people to build a chip dedicated for deep learning on a car. So NVIDIA has been doing that as well with their Drive AGX system. Mobileye is another example of a company which builds an ASIC dedicated for a car. For recommender systems, of course, we have Amazon and AWS, and they have been relying on GPUs for a while, but now I hear they're actually also building their own chip specifically for deep learning in their data centers. They're also specifically building a new CPU for their own data centers, but that's another story. And for NLP and other applications in the data center, there is also, this is an image of a TPU pod at Google, where, you know, various companies are now building their own chip for that. And so maybe I said it like 3 or 4 times so far, but it's important to realize how essential hardware and systems are for the progress of deep learning. They basically go hand in hand. So rewinding a bit back and looking at kind of a very brief history of deep neural networks. So they're actually an old invention. They've been discussed and published and talked about and implemented since the 40s, which is a very long time ago, almost 80 years now. And since the 80s, deep neural networks have been making, you know, tangible impacts. So through the Linnet kind of network in '89, so that was already used for MNIST and worked quite well. So what's missing? Like what happened between the 80s and 2012 that basically really changed the way we think of neural networks, making neural networks kind of colloquial. People talk about, everyone knows what it is, making this huge resurgence in AI and machine learning. So, and as we can see here, 2012 is when, you know, AlexNet was introduced. And what many people don't know is that 1 year before that, there was a breakthrough neural network that also changed the way we do speech recognition. So in 2011, that happened before AlexNet, but AlexNet is the one that was way more popularized. But anyway, so at this point, we had this huge kind of improvement in performance and a huge jump just because of this deep learning technique resurfacing, really, not being reinvented, but resurfacing. So, so a question for you. So why did it take 30 years for DNNs to become useful? So let me see if I can do this thing. Okay, I put a class poll. So hopefully when we're in person, we won't need to do this poll, but for now, maybe if you can give me your responses through that. So. It's cool to see kind of responses coming in. So it looks like most people responded by now. Yeah. Okay, so we had a few people saying that, you know, it might have been the loss function was inaccurate or CNNs weren't invented, but most people actually, so these are not the correct results because the loss function was already the same one we're using today. And CNNs, as I said, were invented back in the 80s with this Linnet, which was the first CNN, as far as I know anyways. And so, so the reason is that computers were too slow. So we needed new hardware. CPUs were focused on kind of branch prediction and building more efficient caches and figuring out the control flow of programs. Whereas deep learning comes in and it's an immensely parallel kind of way of doing computing. It's you can do all of these multiplications and additions in parallel. You don't need to think about if statements or any branches or things like that. And so CPUs just weren't a good match, and that's all we had. And then the other thing is big data. So training data was also insufficient. This was before the time when we had all of these internet users and mobile phone owners generating all of this data that we didn't know what to do with it, really. And so now we have all of this data, and deep neural networks just work way better with more data. And so you need a lot of that for good accuracy. So these are the two reasons. So if anyone asks you, why does deep learning work? Okay, sure, it's a nice algorithm. Backpropagation is telling us how to do gradient flow through the network and how we can kind of propagate incremental improvements throughout like a heavily parameterized function like a neural network. But the enabling breakthroughs really are big data and GPUs. So in the case of AlexNet, Alex figured out how to program a neural network on a GPU. And that was just the perfect fit because GPUs are meant to process lots of graphics. And so graphics is a very parallel application where you have pixels of an image or pixels of an image in a video where you operate on each of those pixels, sometimes independently, sometimes in kind of chunks, so rows of the image or subsets of the image. And so GPUs are really good at doing that in parallel, and that's what caused this huge improvement. Alex Kravitsky was able to kind of scale up the neural network to a much larger size by running it on these GPUs, and then it worked much better. So since those breakthroughs, so around 2012, we've had kind of an exponential increase in the research in this area. So this is showing the number of peer-reviewed AI publications until 3 years ago, and this exponential trend is continuing. I can guarantee it. So academia, that's everything everyone was talking about in the last few years. How do we leverage AI or deep learning to improve my application domain? As I said, whether you're in finance, agriculture, and so on. And the CS community has just been, CS and ECE communities have been exploding with research on how do we create more efficient neural networks and how do we create those systems and hardware for that as well. And sometimes in some topics, it's just academia that's talking about it, but this is not the case here. So this plot here shows kind of the global investment in large corporations in artificial intelligence. And as you can see, over the past 5 years, it's been, again, doubling from, well, more than tripling from kind of 12.75 to 67. That's 5x kind of increase in number of dollars being put behind this technology. So it's not just kind of an academic pursuit. It's a real thing that people are using now and paying good money to make sure it works. So now going back to the again, I want to pause again for people to ask any questions or to make any comments. So I'll stop for 10 seconds. But going back to the kind of example I gave at the beginning, which is speech recognition. So why did those folks at Google sit down and say, we need to rethink how we're doing computing for this seemingly simple application of, hey, Google, what's the weather today, or something like that. So, so looking at kind of a deep learning system example, specifically for speech recognition, you're sitting by your phone and you talk into your phone, you ask it what's the weather, or you're trying to transcribe some text to send it through a message or something. So what happens here? So nowadays, you have some speech data pre-processing that's happening. So you get your speech, you usually generate spectrograms out of that speech data before you send it for further processing. So something happens before any kind of fancy deep neural network, right? And then there's a neural network, but how do you make that run on your phone? And what does that do? So can you actually use Hey Siri or Hey Google when you're offline? I don't know. I think so far we can't. Maybe with the new Pixel chip on these Google phones you can. But I think so far you actually have to transmit that data to a data center to have it processed, and then it comes back. But a big focus for my team back at Samsung was actually how do we take those neural networks and make them function on a mobile phone within reasonable kind of battery usage. So this is a major thing, because if you think about processing in data centers, if you're a phone user and you're using Google, every time you speak through Hey Google or Hey Siri, you're making Apple or Google pay some money. Because there is a power bill for those data centers. It's quite a big power bill, and you're using their electricity. But what all of these companies want is for you to use your own electricity that you charge your phone with at night. So they want you to run those deep learning models on your own phone because it's just an expense to them. So they want to deliver the same user experience, but through your power, basically. And then we can also talk about companies like Samsung that don't have a data center. So they're in the business of creating smart devices for users. And they also want to have kind of a smart assistant. The Samsung one is called Bixby. But then every time you talk through your phone to Bixby, you're actually sending a request to a server paid for by Samsung that Samsung doesn't own. So they pay for both the power of that server and they pay for just the renting that server from a company like AWS or some third-party company. And so running these neural networks on device is a huge topic on its own. And how do we optimize them for that device? How do we build hardware on that device to run these neural networks? And how do we also build the software to compile these neural networks within the mobile programming kind of software framework? And then another consideration on phones is that there is a lot of sensitive data. Like this phone, you have it next to you almost all day now. And you take personal photos, you talk, which are personal phone calls, if anyone still uses phone calls. And so how do you train neural networks through the data on your phone without compromising the security or privacy of that data? So that's called federated learning. And that's also something that we'll cover. So, okay, let's say, we have like a dumb phone that can't do all of these things. We then transmit the data to one of Google or, Facebook's data centers or something. And in that transmission itself, nowadays, there's a lot of AI happening. We actually won't discuss that at length, but maybe someone will choose that as one of their topics if they're interested in communication. But there's a lot of AI-based, communication protocols. So doing channel coding, compression, encryption, and things like that, using deep learning models that happens even as your data is kind of being transmitted from your phone to a data center. So that's also quite an interesting and very emerging topic. And then at the data center itself, we have all of those same questions that we asked at the mobile phone endpoint, but at a data center scale. So, so what kind of hardware do we put there? How do we make it programmable enough but efficient enough, right? What software stack works now for the data center? How can I use those chips in a very distributed way? And there are different examples of doing that in very different ways to train a large model or to map a large model and so on. And then again, everything that happens around the neural network is often overlooked. Some people call it the AI tax. Some people just call it pre and post processing. And this is quite important and needs to be considered when you're architecting your data center. So in each one of our 4 topics, hardware systems, neural networks, and software, I just have a further motivation slide to give you a sense of the urgency of these topics, like why they are super important and why we need to kind of start learning about them right now. I think we still have time. So on the hardware side, I'm showing two plots here. One of them is showing Moore's law, and one of them is showing Dennard scaling. And the summary is that, previously we were able to make computers much faster by just manufacturing a chip with smaller transistors. So Moore's law, what it says is that every 2 years or every 1.5 years or something, we will be able to, in an economically viable way, double the number of transistors on a chip. That means we get an exponential increase of number of transistors, which can roughly translate into computing power every 2 years. So that's like, you're getting a free lunch every 2 years. You're doubling the size of that free lunch every 2 years. But there's obviously a lot more involved here, and that's a main constraint there is power, and that's what Dennard scaling kind of explains. And what Dennard scaling states is that every time we shrink the size of the transistor, the power density stays constant. So what does that mean? So we have double the number of transistors. We used to have 5 transistors in this piece of the chip. Now we have 10 transistors in that piece of the chip. They will use the same power. Maybe it's 1 watt or something, as an example. But that actually started to break down. So, and break down in a very bad way. So we can see here, we're doubling the number of transistors on chip, and power density is staying approximately constant. So that's the power per area, right? But then around 2008, it just goes haywire. It just explodes. The power density increases dramatically. And the reason is that, we were hitting fundamental technology limits of silicon and of transistors. We're getting something called a tunneling current and lots of parasitic effects because we're making those transistors so small. So you're getting a lot of kind of wasted electrons going off in different places where it's not supposed to go and generating heat. And basically that has severely limited the utility of those extra transistors that we put on chip. So even if we put, I don't know, like 1 million or 10 million transistors on a chip, we're only able to use 5 million of them at a time, just because of this power constraint. And if we look at the Moore's law curve as well, the actual thing is this red one. So it's not really tracking the original 1975 version of the law. And I mean, Gordon Moore himself, he says, there will be fundamental technology limits that slow down this Moore's law. All that's to say, we're not getting faster chips for free. And what does that mean? So if we can't get faster transistors through silicon or by improvements in the silicon and the process, then we have to resort to architecture. We have to think of smarter ways of using the transistors we have on the chip. And usually what that leads us to is that we're not creating these general purpose chips anymore. So we're not creating a CPU that can run any program, right? No, we're creating these domain-specific architectures that are focused on a specific application domain, and therefore we get the efficiency that way. We specialize the transistors to do only deep learning or only deep neural networks, and that's how we can get kind of an improvement in efficiency. So we're not getting it through the technology, we're getting it through architecture. And so hardware architecture is having this huge resurgence now in terms of just the number of people studying it, number of people interested in it, the amount of research happening in hardware architecture, because basically we have no other choice. We can't just keep making chips faster. We have to think of smart ways of putting those transistors together. And that wasn't the case for the past 50 years, basically. And then, so that's hardware. Another topic, like I said, we will look at neural network compression. And what I'm showing here is, 5 years gap between state-of-the-art deep neural network for vision, for image classification, VGG16, And now the state-of-the-art one is EfficientNet, maybe at a low flops count anyways. And so we're seeing kind of, what is this, 3 orders of magnitude reduction in the number of operations that we need to do. So forget hardware, like even at the neural network level, just designing how we do these neural network operations, we're able to get so much improvement through these techniques listed here. So, quantization, pruning, neural architecture search, various scaling methods, and so on. Basically, people are still trying to figure out how to build the topology of those neural networks. How do we organize the computations in a neural network to get the most efficiency while maintaining accuracy? And there's huge potential there. We're basically just scratching the surface. Because if you look at those 2 neural networks, they actually look quite similar. Okay, maybe some of the primitives are a bit different. We're using separable convolutions instead of regular ones. We have skip connections. There is some automated neural architecture search to figure out exactly the parameters of the neural network. But this results in a huge drop in computation. Same is true for kind of the model size. Again, orders of magnitude smaller. And accuracy has actually improved over those past 5 years. And so this is a major area of study and a major source of getting more efficiency for these neural networks. One of the projects we worked on at Samsung is doing super resolution. So basically, Samsung creates these displays, these TVs, 8K and higher, and there is no content that runs in 8K. So what do? They have a chip inside the TV that takes all of kind of the incoming streams of video, and they're automatically upscaling to 8K. And so how do we run? So these super resolution networks are huge. They're very big. It's very hard to run them on a TV with the computing that we have on a TV. You either stick, an NVIDIA GPU at the back of your TV, which would be very loud, very hot, or very warm. It would make your room very warm, and it will be very expensive to run as well. Like your TV will suck so much power, it won't adhere to any standards out there that are set for TV power consumption. And so the alternative is to build a very efficient chip, but also to compress the super resolution neural network. So we worked on one of those neural networks, and we got a 30x reduction in flops, just based on applying some of these kind of now well-known techniques, like pruning and quantization, and definitely neural architecture search, which I was focused on Samsung. So these techniques really do work even today after all of these hand optimizations have been done. And it's a major thing that we'll focus on. So software. So I have a bunch of logos here, and there are many more out there, basically on different frameworks, domain-specific frameworks, domain-specific languages, and domain-specific compilers that are dedicated to deep neural networks. And how do we both specify these neural networks at kind of a program level? How do we compile them and map them onto hardware as well? And so, I'll be impressed if someone knows exactly what all of those logos are, but at this point, in this lecture, but I would be, by the end of this course, you will know what all of these frameworks are, how they work. Well, not all of the details of how they work, but basically what the concepts are behind them, and why we are even resorting to these domain-specific languages. And then on the system side, we have many considerations there, and 2 of the ones that we'll focus on is federated learning and distributed training. So distributed training is quite interesting because there are many ways to do it. As I said, one of them is to replicate the model over multiple computers and then split the data, because you have so much data as well among those computers. So you will have one computer learning from a quarter of the data, another computer learning from another quarter, and then you'd have kind of 4 computers cooperating. And then the question becomes, how do you send the gradients during training between those computers? How do you divide the work up? How do you synchronize all of your parameter updates and so on? And then another kind of distributed training is obviously if you have a very large model, so all of the parameters can't fit on one device. So then you need model level parallelism as well. So you split your neural networks into pieces. You put each one of them on a different GPU or a different machine. Doesn't have to be a GPU. And then how do you do training in that case as well, where you will need to propagate both values during the forward pass and the backward pass as well. So federated learning, which I actually know less about, but it's quite an interesting topic, is when you have multiple users, all with these security and privacy constraints, how do you learn from the data on their devices? And so hopefully I might actually get an expert on this to give a guest lecture, because I know someone working at Facebook who's a great person and an expert on this topic. But at the same time, I think this kind of research will only increase because of the things I said before. Data is being generated on the user side in these plethora of devices that are in the hands of users. And it's in the best interest of these large corporations and large companies like Google and so on to perform a lot of the computations on the device side. Of course, they'll tell you it's because of security and privacy, and I buy that, but it's also an economic thing on their side where they want you to pay the power bill, not them. So, okay, so yeah, that's again this slide that I made for the topics that we'll cover. So this is the order in which we will cover them. We'll start with hardware, move on to neural network optimizations, and then software. And finally, we'll talk about systems. This is the order that I think makes most sense. I want you to have a hardware-centric thinking throughout this course, and that's why we're starting with hardware. And then, yeah, I just think it makes more sense to go this way. Again, if there are any questions so far or any comments, maybe someone out there is sitting, oh, this is not what I expected this course to be. This is really, or no, does it all make sense? Let me see the chat window. Chat window is empty. Okay. I'm assuming silence on Zoom is a good thing, but hopefully in 2 weeks' time, you guys will be here, and then I'll be able to read facial expressions as well. So, I mean, behind the masks, of course. Okay, so I mean, I'm basically at the end of this lecture. I think we have 10 minutes. So the next few minutes, I'll just talk about assignment 0 quickly. So this one is just about knowing your design tools. It will be released today. So again, if you don't get a link, or if you're unable to access the assignment, or if you if you get nothing, basically just let me know. And it's a very simple getting started assignment. As I said, we're going to use Google Colab. What that does is that it instantiates a Jupyter notebook on one of the computers that sits in Google data centers. And once kind of you close that tab or your session ends, everything disappears. And so this assignment 0 will go through how you can mount your Google Drive folder to have that as your virtual file system, so that any files that you produce during your assignment, they get stored there and they don't disappear, instead of storing them to this random Google machine, which wipes everything once you leave your session. Does that make sense? I'm hoping that makes sense. So that's one of the things you'll learn how to do there. And it's a bit, it's not tricky, but it's a bit annoying to always kind of mount the Google Drive folder and figure out exactly how to do it and where to store stuff. And so this assignment just walks you through it, and it becomes kind of a standard thing you do at the beginning of every notebook. And that will give you more of a local development experience while you're using Google Colab, instead of this kind of ephemeral vanishing file experience that you get with when accessing kind of a cloud machine. And so that's one thing that you'll learn there. You'll also learn how to interact between GitHub and your Google Colab notebook. So as I said, the assignments will be on GitHub Classrooms. And there you will submit all of the code. So basically you will get an assignment a template repository that will have all of the steps that you need to go through to complete the assignment. And then this same repository will also have starter files. So a starter Jupyter notebook sometimes just source files and tests and so on. And then you will work on those files and you will commit your code and push it back to the same repository. And this is what I'll grade. So I will see all of your pushes and even you can do a pull request and ask me questions and so on. But we can also use Ed discussion for that. But yeah, so this assignment will also focus on connecting your GitHub account to Google Colab, pulling the assignment, working on it, making a change, pushing back the changes, and all of this, all of these small details. It's also, as I said, this assignment is worth 2 marks. I'm hoping everyone in this course will take those 2 marks. It's not meant to kind of test you or anything. So there are questions. If we are, okay, let me just finish my thought and then I'll go through these questions. So think of this assignment as an opportunity to kind of just ask questions early on. Make sure you understand exactly how your development environment works. If you want to pay that $10 for Colab Pro, feel free to do it. You can also start paying for that on assignment 2. That's the main one that will require those $10. But as I said, if you don't buy it, it doesn't matter. And it's also a subscription thing. So if you want to stop it right after assignment 2, you can always do that. But it's cheaper than a textbook. Think of it that way, and it might make your life easier in assignment 2. But yes, ask all the questions you have about the development environment. Use Ed discussion, please. Use it heavily. That's the main way to get in touch with me or the TA or your colleagues, which will be a good resource to ask, questions. Don't give any answers or any kind of things away on Ed discussion, obviously, but that goes without saying. Yeah, so I see here a couple of questions. So Ethan, if we are on the wait list, will we still be able to do the assignment? We'll be able to enroll soon. So hopefully you'll be able to enroll soon, Ethan. If you have any concerns with that, please email student services and CC me so that I can follow up. I think we don't have many. I think we have 5 people on the wait list or something. And so I might try to get student services to just add them if the classroom fits. I mean, I don't mind the extra 5 people, of course. Yes, you'll be able to get the assignment. If you don't get a link today, just email me or post on Ed discussion, a private post or something. Let me know and I'll send you the link. It's that simple. Even if you're auditing this course, let me know and send me the link. When it comes time to grade the assignment, I'll only grade people who are actually registered because it doesn't make sense to grade people auditing and stuff. They don't need a grade. But you can definitely work on the assignment, that's fine. Any resource you'd recommend to refresh on computer architecture? Yeah, so obviously the canonical textbook is Computer Architecture, a Quantitative Approach, I think it's called. Basically the Hennessy-Patterson book. And I might actually assign one of the chapters there for you guys to read. But yes, so I recommend Hennessy-Patterson computer architecture book to brush up on Comp Arch. But yeah, so it's good to read that. The first reading is actually quite nice. It's called The Golden Age for Computer Architecture, I think. And then yeah, this is the reading. It goes through how we shifted from this kind of following Moore's law to these domain-specific architecture. And it's a good summary, and it's written by Hennessy and Patterson, this article, by the way. So it's a good summary of their book, actually. So it's like a, I don't know, 10-page or 5-page summary of their book, basically. But yeah, for reference material, I really recommend that book as well. James Ann, are we required to use Google Colab versus local? So you are not required to use Google Colab. So the reason I'm having you use Google Colab is just so that you have a GPU to access, basically. If you want to use a local Jupyter notebook and you have access to a GPU, by all means, please do that. I have no problem with that at all. For all of the assignments that require knowing which device you're running on and stuff, I just ask in the assignment handout, which device are you running on? Like which GPU device or which CPU device and so on. So you can use your own machine. The only thing is the course material is designed for Google Colab. So I will not have two sets of assignments, one for Colab users and one for non-Colab users. So everything will be designed for Colab users. So you have to figure out all of the small details around running it locally yourself, basically. But if you can figure those out, that's fine with me. And they are very minor things. So if you're used to running neural networks locally and stuff, then you'll be fine. Okay. Yeah, I think this brings me to the end of the lecture. And so I think we have, I actually don't know when this lecture ends, but I think it's in 5 minutes. So we have 5 minutes for questions or discussions or just saying random things yeah, like whatever, if anyone has anything on their mind, basically. So this is the first reading. One more note is that we will also use Gradescope. I don't know if people used it before. Has anyone actually used Gradescope before? You can just unmute and let me know. Yes, people say yes. Good, because I haven't used it before. So the assignments will be there. Each assignment has 2 sections, or 2 things to hand in, really. Every assignment, this doesn't change. One of them is a write-up. So this explains what you've done, answers to all of the questions that need a text answer. And you would also copy a lot of the graphs or numbers you produce in your notebooks into this write-up. So the write-up should be a self-contained thing. I should be able to sit on my chair, read this write-up, and understand stuff that was assigned. And so all of that, all of these write-ups will be submitted on Gradescope. And so I already created like a placeholder for A0 and a placeholder for the weekly readings. So also the weekly readings, this short paragraph summary, that should be submitted through Gradescope as well. Whereas the code should be functional. It should include all the code you used to answer the questions in the assignment. And that should go onto GitHub Classrooms. Okay, so 2 things to hand in, GitHub Classrooms and Gradescope. Write-up and code. So yeah, okay. Okay, yeah, that's all I have. Any last questions or thoughts about the course, about me, about Cornell Tech, about what happens in 2 weeks? So in 2 weeks, you guys should come into class here. The general policy is that you have to attend class in person. We have a mask mandate, obviously, so you should be masked. And if you want, but there will be also, the Zoom link will be functional. If you want to attend on Zoom, you should have an excuse and you should let me know before that. So yeah, you should come in person. Obviously, also not coming in person means you have no chance of getting those 5%, those almost free 5% of the class participation. So exciting course. Good. Great. Thank you, Sri. Sri thinks the course is exciting, and that's good to hear. That's the main reason for this first lecture, is to get you excited about the course. Okay. All right. If you're in any doubt, go to the Ed discussion, ask questions there. For all of the links and stuff, again, the course website is your resource. And I think we can then just end here. I think that's everything I have for today. Okay. Okay. Thank you, everyone, and see you in 2 days. Thanks.